In last lecture, we looked at how to put two Poisson processes together in a sense like the concept of addition. And here we look at another example. We can actually take part of Poisson process, but which part to take, it has to be random. And this way we have really just a percentage of Poisson process, and it still is going to be a Poisson process. So let's look at the guideline first. Suppose we have a Poisson process NT, and we have a rate R, and Tn will be the nth arrival time, and let Xn be an IID random process having a Bernoulli distribution. So Bernoulli distribution, remember, is either 1 or 0, and the probability that Xn is equal to 1 is P, independent of the Poisson process. Now, let Yt be the number of arrivals counted in the following way. So if Xn is 1, then the nth arrival is included in Yt. If Xn is 0, then the nth arrival is not included in Yt. Now think about this is like the following experiment. If you have, say, customers coming to a store, and whether or not to count the customer as an arrival, you flip a coin, an unfair coin. If the coin shows heads, then you count the customer as an arrival. If the tail shows tails, then you say it's not counted. So in this way, if you just count those customers that your coin shows heads, then it's a portion of the actual arrivals. And again, we have a Poisson process. And of course, the rate is going to be smaller, so the rate is going to be P times R. Okay, that's what it means, the decomposition of a Poisson process. So let's look at a simple example. Customers arrive to a store according to a Poisson process with mean rate 5 per hour. So 5 customers per hour. The probability that a customer leaves without spending anything is 20%, is 0.2. Let Yt denote the number of customers that spend something in the interval, time interval 0, 1. Determine the mean and variance of Yt. Now if you think about this one, even though we are not flipping a coin, you can think about when a customer arrives, whether to spend in the store or not. It's like flipping a coin. So here 0.20 means that these 20% customers are not going to be counted as actual spenders, you can think, or actual arrivals. So what we have over here is really a decomposition of the Poisson process. So we can see the following thing, that imagine that we have the nth arrival, okay, and we have 20% chance is not going to spend anything, not to spend anything. And then we don't count, do not count. And we still have the rest of 80% that will spend something. Will spend something. And then this one is counted in Yt. So Yt is part of Nt. So you can see Yt is essentially 80% of Nt. But this 80% is counted in a sense randomly. You don't know which one is going to spend, which one is not going to spend. So
if you want to find out the rate over here, the lambda, or you say over here is r, and it's going to be 0.8 times 5, and that's going to be 4. Of course, we can intuitively get that's the rate of arrivals of customers that will spend something. So this is number of customers who spends, we say spenders, okay, per hour. And if we want to find out what's going to be the expected value of y1, that means time is 1 over here, and that's going to be simply 4. Okay. How about the variance? Now let's try to remember that the variance we have for the Poisson distribution, the variance of the Poisson distribution is also lambda. So we know this is the same thing. It's also the lambda over there. So we have, again, it's going to be 4. All right, so this is a rather short problem. It's about part of it. Later on, we are going to actually calculate what's going to be the expected value of the revenue if we know the behavior of these customers who spend money in the store. Okay, so this is only part of the problem that we're going to deal with later on.